Hi, welcome back to the course Foundations for Machine Learning. We are continuing to learn some mathematical foundations. In this lecture, we will look at some fundamentals of probability that you need to be aware of if you want to become a serious machine learning engineer. This lecture is aimed specifically for beginners. So some of the concepts, if you are very familiar with probability, you will find very trivial. But if you are a beginner or if you are learning for the first time, you will definitely enjoy this. So let's try to understand some basic concepts without going into the extreme details of probability, which we may not need when we are further going ahead and learning machine learning. So first, I want to emphasize on the fact that two most important things that are needed in machine learning is conditional probability and Bayes theorem. So when we say fundamentals of probability, we'll be focusing primarily on conditional probability and we'll be diving deep into Bayes theorem. It's a little bit confusing. When I learned Bayes theorem for the first time, it was, although the equation was very simple, the physical intuition behind that, mapping that intuition with the equation was always very confusing. And whenever some problems were asked, it almost always caused confusion. So I did not feel very comfortable while learning Bayes theorem for the first time. But as the intuition grew deeper, I realized there are easier ways to think about and understand Bayes theorem. So I'll try my best to kind of transfer that idea to you. So let's do a quick recap. A probability of an event E, P of E, is the number of favorable outcomes divided by total number of outcomes. So if the experiment that we are performing is rolling a dice, and if the event is described as the occurrence of number 4, then the space, the entire experimental space is 1, 2, 3, 4, 5, 6, and the event space has only 4 as the number. So it's basically this space, length of this space divided by the length of the actual entire space of outcomes. So it's 1 divided by 6. So these are some formalities, but this is a fairly easy thing to even understand. Probability for any given number when you are rolling a normal dice is 1 by 6. This is the quick recap. We don't want to go into it any further because these are simple mathematical definitions. Now, where is probability exactly used in machine learning, especially conditional probability? This occurs almost always because in real world there is uncertainty. If you have data set about an email, let's say the words or the text contained within the email, and you want to perform a classification based on the text within the email, that whether this email is a spam or non-spam. And you might have some data from real world that if these words are part of the email, it is very likely spam. But then this word very likely has to be quantified, because at what point will you decide that the occurrence of certain words in an email will make you classify that email as spam? So let's say you are Google and you would like to develop a automatic spam filtering, so that your inbox, like your user's inbox, is not getting cluttered. So when you are designing this algorithm, in the spam filter, you have to put some condition, right? If the probability of an email being a spam is greater than, let's say, 90%, 95%, you decide some cutoff or threshold. Then you say, move this email to the spam, otherwise keep it in the inbox. But then to decide, to calculate that probability itself, you have to have some real world data. And in real world, the data is almost always uncertain. So to deal with this uncertainty, conditional probability will help you quantify that. And in ML algorithms, things like naive Bayes classifier, which is very commonly used, even in one of the papers that we published recently, one of the models that we used was naive Bayesian classifier. It directly relies on conditional probability. So this is core to many traditional ML algorithms. Even when you are interpreting the working of a particular ML model, there are concepts like, if you have a image classification model which you built for, let's say, some healthcare data set like brain tumor identification, and if your ML model is performing with certain degree of accuracy, let's say 99% accuracy, that is also not enough, because you need to know how many true positives and how many false positives are there. So given an image, if a brain tumor is actually present, with what probability will your ML algorithm identify that? and with what probability it will not identify that. On the other hand, if the brain tumor is absent, with what probability will the ML algorithm falsely recognize that there is a tumor, and with what probability will your, or with how frequently would your ML algorithm classify something without tumor as no tumor. So there are different combinations like this, and having a fairly good understanding of the probability of occurrence of an event and another event followed by this event will help you quantify what is the actual expected probability of a certain event. So I don't want to speak more in vague terms. I want to give you some specific examples. So before going into all of that, it's very helpful if you know a little bit of probability related rules, and thinking of probability as or these set diagrams like Venn diagrams. So there is something called addition rule in probability, P of A union B, which is the probability for event A or event B to happen. So it's not and, it's or. It is probability of event A plus probability of event B minus probability of event A intersection B. This is also easy to visualize if you have the help of Venn diagram. So if this is a circle, another circle, and let's say this is A, this is B, P of A, P of B, and this is in between is P of A and B, which is A intersection B. Then the probability for A or B to happen is you add the probability here, you add the probability here, but then you are counting the middle region twice. That's the reason why you have to subtract A intersection B once, because within P of A, there is already P of A intersection B. Within P of B also, there is P of A intersection B. So that's why when you add these two, you are double counting the P of A intersection B, but you have to count it only once. So that's why you are subtracting P of A intersection B once from this. So this is a good way to visualize. Now let's take an example. Let's say a dice is rolled. What is the probability of rolling an even number or a number greater than 4? So basically we have two events here. We are describing two events. The event one is even number, getting even number, which is 2, 4, 6. Then we are saying or a number greater than 4. So the probability of event 1 is 3 by 6 because you have three options, 2, 4 or 6. So but there are total 6 outcomes. So the probability for event 1, which is even number, is 1 by 2. The probability for event 2 to happen, which is having a number greater than 4, there are only two options, 5 or 6. So that is 2 by 6, which is equal to 1 by 3. But then probability for event 1 or event 2 to happen is not simply 1 by 2 plus 1 by 3, because there is also one case where event 1 and event 2 can happen simultaneously, the intersection, which is if 6 occurs, because 6 is belonging to even number. So if 6 is coming, it's event 1, but 6 is also greater than 4. So if you get a 6, then you satisfy both criteria of being event 1 and being event 2. So basically probability of event 1 and event 2 happening is having a probability where you have an even number and you have a number greater than 4, which is only when you have a 6, which is only 1 out of 6 cases. So that's why it is 1 by 6. So now if you want to find the probability of event 1 or event 2, you add the probability of event 1, which is 1 by 2, plus probability of event 2, 1 by 3, minus probability of event 1 and event 2. So this 1 by 6 is the intersection. So in this, P of A would be 1 by 2, P of B would be 1 by 3, and P of A intersection would be 1 by 6. So now probability for A or B to happen is 1 by 2 plus 1 by 3, which is 5 by 6 minus 1 by 6. So that will be 4 by 6, which is equal to 2 by 3, which is what you have here. So this is the addition rule of probability. There is one more rule, multiplication rule. So this is probably a bit more confusing than the addition rule, especially if you haven't thought of probability in this particular context. In the multiplication rule, we are finding probability for A and B. So two events happening simultaneously. It is probability for A to happen multiplied by probability for B to happen given A has already happened. So this notation P of B vertical bar A is read as probability of B given A. So that's how you read this. That's what I have spelled out here. Probability. So P for probability, P of B given A. So this is the probability for event B to happen given A has already happened. So the probability for A intersection B, which is probability for event A and event B to happen simultaneously, is the product of these two. We can also come to the logical reasoning behind that really soon. In ML, there are use cases where if you are trying to model joint probabilities in certain decision making, an example of B given A is, let's say you are building a advertisement, you are designing an advertisement, and you would like to quantify the probability for a user to see an advertisement, and then given the user has seen the advertisement, how likely are they to click? So A could be, the event A could be description of user seeing the ad, and B could be user clicking given they have seen the ad. So now P of B given A is given the user has seen the ad, how probable are they to click? Simply P of B means user clicking. So they would be clicking through seeing the ad. They could be clicking from elsewhere. Clicking meaning clicking to get into the website, if that is the advertisement, if you're advertising a web page. This is the physical interpretation of P of B given A. Now let's take an actual mathematical example which you might be familiar with. So if we have a deck of cards, what is the probability of drawing two aces consecutively without replacement? So what this means is you are looking at two events. Event 1 is initially drawing an ace from a deck of cards. Then event 2 is the initially drawn ace is not replaced. It's kept with you. So you're not putting it back into the deck. Then the event 2 is basically drawing another ace from that deck. So here we have two events. That's why I have written here event A and event B. So event A is simply getting an ace from a deck of cards. There are 4 aces and there are 52 total cards in the deck. So the probability for this is 4 out of 52. But event B is happening after event A has happened, right? So we are not looking at event B just as drawing of a single ace. It is such that P of second ace, given first ace was already withdrawn. This is what we are looking at. So we should not say that the probability for second ace is 4 out of 52. We have to consider the fact that this has already happened in this particular situation. So now we have 53 cards because one ace is already withdrawn. Sorry, not 53, 51 cards, because from 52, one is gone. So total, you have 51 cards and you have only 3 more aces available because one of the aces out of these 4 is already taken. So now when the event A has already happened, the probability for event B to happen, P of B given A, is 3 out of 51 because you have only 3 aces to withdraw and you have a 51 deck card. Basically you have a deck of 51 cards. Now the question is it's not about event A or event B. The question is about both of these events happening one after the other. So the combined probability of event A as well as event B happening. So if you want to calculate the probability of event A happening, it's 4 out of 52, right? So if I write it in words so that you can understand it a little bit better, because I don't want you to get confused here thinking what is A and what is B. So probability of first getting an ace and second also is an ace is equal to probability of first getting an ace multiplied by probability of second card also being an ace given first card was already an ace. the first pulled card was an ace, right? So first was an ace. So now what is this? This is equal to, so the question is asking this, and probability of the first being an ace is 4 out of 52. Probability of second being an ace, given first was already an ace, which was pulled and which was not replaced. Now this is 3 out of 51. So now the answer that we are looking for is 4 out of 52 multiplied by 3 out of 51 equal to 12 out of 2652. I did not do this mental math. I saw it here. I had already calculated this, and this turns out to be 1 out of 221. So this is how you have to calculate the probability. This notation of P of B given A is already within conditional probability. In the coming section below, we are diving deeper into conditional probability. So don't be worried if you are not too familiar with this notation or with this concept. You will understand it better. There is one more rule that you should be familiar with. It's called complement rule. So here, this is not called as A prime. You can call it as A prime, but basically it is A complement, meaning the opposite of event A from happening. So the probability for the opposite of event A to happen is 1 minus the probability for event A to happen. So now if it's a coin flipping, if head is an event, the opposite of that event is tail. So now let's say we have a question. A coin is flipped twice. You flip it once and you again flip it again. So what is the probability of getting at least one head? So this is the event that we are describing. But what is the opposite of this event? The opposite of getting at least one head is not getting any head, which means both of them are tails. So let's say event A is that event where you don't have any heads. Basically both are tails. So then it is the probability for event A to happen is getting the probability for getting a tail first multiplied by probability for getting a tail second. And since the probability is unaffected, with the second toss is not going to be affected by the previous toss, then the probability for getting two consecutive tails, tail and tail, is 1 by 2 multiplied by 1 by 2 equal to 1 by 4. So the event A, which is probability for no heads, 0 heads, which is the exact opposite of at least one head, is 1 by 4, which means the probability to get at least one head is 1 minus probability to get no heads. So it will be 1 minus 1 by 4. So it will be 3 by 4. So 3 by 4, with 3 out of 4 chances, you will have at least one head in your total event of 2 coin tosses. So this is based on the complement rule. All right. Now we can formally get into conditional probability. This is probably the most important concepts that you should understand from probability out of all the other things. So let's have a look at the formal definition. So the formal definition you already saw above, but I want to reiterate it a little bit here. So the conditional probability is nothing but probability for an event A to occur given event B has already occurred. So probability for someone to click an ad given they have already seen the ad. Probability for an email to be classified as spam given the email has certain set of words. Probability for let's say a machine learning model to classify an image as having brain tumor given the person actually has brain tumor, meaning the image is actually that of someone with a brain tumor, because the ML model can be inaccurate also. So these are conditional probabilities, and in real life you almost always only encounter conditional probabilities because you have a cascade of conditions often. It's never a simple probability. So that's the reason why for real life problems which machine learning often deals with, you have to be very familiar with conditional probability. Now the equation that describes conditional probability, it is P of A given B equal to P of A intersection B divided by P of B. This A intersection B can also be read as P of A and B to occur, both to occur. And this is valid obviously when P of B is not equal to 0. And because if P of B is 0, then this thing has no meaning, because If B has zero chance to occur, then there is no point in saying something like probability for A to occur given B has already occurred. If P of B equal to 0, then there is no meaning in saying given B has already occurred. B cannot occur. So that's the logical reason why conditional probability will not have meaning if P of B is equal to 0. Mathematically, it's because if P of B equal to 0, you are dividing by 0, which is invalid. Now, there are several ways to understand the logic behind this formula rather than just by hearting this. But the best possible way, at least the one which I think is the best way, is using these Venn diagrams. So here, this is this first circle represents the probability for event A to occur. So let me write it as P of, otherwise it might be confusing. So this first circle represents P of event A. Then the right circle represents P of event B. And the middle intersection point represents P of event A and B to occur. Now, what are we talking about in conditional probability? We are saying that B has already happened, right? This guy B has already happened. Meaning if B has already happened, then we are looking at this exclusively. We are looking at this circle. So we are given the information that B has already happened. So this has happened. Now, if that is the case, what is the probability for A to happen? So what fraction of this has the presence of A in it? The presence of A is there only in this, right? Because this is the A intersection B region. So the fraction of this circle which has the presence of A is only this intersection portion. So, and how do you represent that fraction? You represent that fraction simply by dividing whatever is this by that of the total circle. So what is intersection? It is nothing but P of A intersection B. That is the size of the intersection region divided by size of the total region. Size of the total region is nothing but P of B. And what are we calling this? This is nothing but P for A to happen given B has already happened. So in my opinion, this Venn diagram based thinking is the easiest way to think about conditional probability instead of trying to remember these equations, because equations will make it very confusing. And I'm sure after going through this lecture, maybe after a few weeks you will completely forget the equation. But if you visualize the conditional probability as these Venn diagrams, it's very logical, and then you can derive the equation from that. So just keep this image in your mind. Basically, we are in the universe where B has already occurred, which is why I shaded this circle corresponding to P of B. In that, what fraction has A, or what fraction is A? The fraction is only P of A intersection B divided by P of B. So this is the basic intuition. So I hope that makes it, that brings more sense into this formula which describes the conditional probability. Now, conditional probability allows us to make some new predictions, because usually what is P of A, if you were asked just what is P of A, it is this full circle. However, when a new condition arises, let's say the new condition is that you are told that B has already occurred. Now what is the probability of A? That's when you come to this fraction. That's when you come to this conditional probability, where you take the ratio of whatever is this, which is P of A intersection B, divided by whatever is this, which is P of B. And this is what happens in real life, right? In real life, the information will get updated. You may receive the information that something has already happened, and now you will have to calculate the probability. A really good example to think of is, let's say there is a cancer test, and this test has 80% chance of detecting a cancer in case a cancer is already present. But then if a test is giving you positive result for a cancer test, let's say 80, is it true that you will definitely have 80% chance of having cancer? No, because the test can give false positives also. So if it may have 80% chance of giving you true positive, but it may have like a 10% or 8% chance of giving false positives also. Even in the case when you don't have cancer, these tests might sometimes say that you have cancer. So conditional probability allows you to kind of make a rationale whenever you have these results. Whenever your model is saying something, if you have conditional probability, you can make sense out of it. Now let's take an actual question. So you have a bag. The bag contains 3 red balls and 2 blue balls. So totally 5 balls, 3 red and 2 blue. Now you are drawing one ball, you are not replacing, and then you are drawing another one. So you have 2 events. Event 1 is drawing one ball, event 2 is drawing another ball. But between these 2 events, you are not replacing the first ball which is drawn. Now the question is, what is the probability that the second ball is red given the first ball was red? So you already drew like a red ball in the beginning in the first event. Then what is the probability that the second one is also red? So event A is withdrawing of red ball initially. That is fairly easy. P of A, where event A is getting red ball in the first draw, it's 3 out of 5 because you have totally 5 balls and you have 3 red balls. Now the second one we are looking at is event B given A. So what is B? B is also getting a red ball given A has already happened, meaning given the first draw already gave a red ball. So second is red ball given first was red without replacement. I'm not saying that, but just understand that we are not replacing. And then let's also discuss, before calculating this P of B given A, let's also discuss what is A intersection B, meaning A and B happening. So this is fairly easier to calculate because P of A to happen is 3 out of 5. And P of B to happen is then 2 out of 4. Just P of B to happen. And so the probability for A to happen first and B to happen next is 3 by 5 multiplied by 2 by 4. Because initially there are 3 red balls, you are drawing it from a set of 5 balls, so 3 by 5. But then once this has happened, the probability for the next event also to happen simultaneously is 2 out of 4 because you have now only 2 red balls and you are drawing it from totally 4 balls. So this will be 6 by 20. But this is not what is being asked, because 6 by 20 is not the probability for the second ball to be red. This is the probability for first ball to be red and the second ball to be red. Now let's try to calculate what is the probability for the second ball to be red given first ball was already red. So for that, P of B, B which is second ball to be red, given A which was first ball was already red, is equal to P of A intersection B divided by P of A. And why is that the case? Because this is the probability for first ball being red. This is second ball being red. This is first and second is red, right? This intersection. And now what we are being asked is, given the first ball was already red, what is the probability that second ball can be red? And that is clearly saying that this has already happened because first ball is already red, that this information is given. So now we are looking at this circle. And then we are being asked, what is the probability within this circle? What is the probability for the second ball also being red? And what is that? The second ball being red within this circle, the region that corresponds to that is this. So now it is the ratio of the intersection region to this. And the intersection region is nothing but P of A intersection B. And the shaded circle is nothing but P of A. And P of A intersection B, we know that it is it was 3 by 5 multiplied by 2 by 4, which is 6 by 20. And P of A, we know that it is 3 by 5. So this will come down to, so this will be 3 by 10 divided by 3 by 5, which will be 1 by 2. Yeah, so that is what it's here. So 1 by 2 is the probability for the second ball to be red, given the first ball was already red. This is a very simple problem. You may feel like it's unnecessarily complicating because if the first ball is already gone, you know that only 2 more red balls are remaining and there are only total 4 red balls. total 4 balls. So it is 2 by 4. You can easily mentally calculate it, but as the problems get complicated when conditional probability is being asked, you will almost always get the answer wrong. It's very confusing unless you think of it in a methodical way. Now let's come to the last part of this lecture, which is Bayes' theorem. I originally wanted to combine the conditional probability lecture and Bayes' theorem lecture into one, but I realized that it is better if I spend one entire lecture on Bayes' theorem because I want to walk you through a very interesting example. But nevertheless, since we are at the end of this lecture, I want to touch upon Bayes' theorem, give you a fairly good insight about this, and then in the next lecture, I want to talk in detail about the Bayes' theorem. So Bayes' theorem, just mathematically what it says is the probability for A to occur given B has already occurred is probability for A to occur multiplied by P of B given A divided by P of B. Now, this is not at all intuitive. It's very, very difficult to make logic out of this formula. So now let us look at this from a very simple example perspective. So let's take a machine learning application. You want to create an ML algorithm for filtering spam. So if you are getting an email into your inbox, you want to classify whether this particular email is spam or not spam, right? So how do you think about this? Let us take a specific example of a famous spam email with Nigerian prince. So you can Google Nigerian prince spam email. It's actually not spam, it's also like a scam, but basically the content of the email is something like this. Dear sir, I am Prince, someone from Nigeria. Your help would be very appreciated. I want to transfer all of my fortune outside Nigeria. Outside, if Nigeria refers an account, so if you would be kind to transfer a small sum of 3,500 USD to my account, I will be able to unfreeze my account and transfer my money outside of Nigeria. To repay your kindness, I will pay 1 million USD to your account. So this is one email. I have definitely received this email many years ago. These days, this email is not that common. Where else is there? Yeah, basically this one only. Like a Nigerian prince reaches out to you to give them some small amount of money to solve their issue, and in return they will give you a large sum of money, right? So this is like a classic scam / spam. So let's say you receive 10,000. You have total 10,000 emails, 10K emails total, right? And let's say out of this 10K emails, 100 belong to spam category, and let's say remaining, what is it, 9,900 belong to not spam category. Now in these 100 spam emails, imagine that 90 emails contain the word, 90 emails have the word Nigerian prince in it, okay? And 10 emails they do not have the word Nigerian prince. And what about these 9,900 not spam emails? In these 9,900 not spam emails, let us say 50 of them have the word Nigerian prince. And remaining, what is the number? 9,850, is it? Yeah, 9,850 do not have the word Nigerian prince. Let's say this is the case. And now you might be wondering, how can a not spam email contain the word Nigerian prince? Let's take a example thinking that, okay, maybe someone is trying to educate you that if you receive an email like this, it is a spam. So let's say these 50 are educational emails, right? I'll just write it here so that it's clear. So these are educational emails. So you don't want to design a ML machine learning based spam filter which will classify this also into spam. Now, let's say the goal here is the following. You're asked a question. Given an email contains the word Nigerian prince, calculate the probability that the email is actually spam. Right? This is the question. Now we have two events here, right? Event A is something being spam. Event B is having the word Nigerian prince in the email, right? So these are the two events. Now what is asked is to calculate probability for event A, meaning something to be spam, given B, meaning Nigerian prince is there. Now we can of course calculate it mathematically if we were to use Bayes theorem, but that is not my goal here. I'll write it anyway. This is nothing but P of B given A multiplied by P of A divided by P of B. Right? So what the Bayes theorem says is over here, P of A given B is P of A by P of B times P of B given A. So what I have written here is also the same thing. P of A given B is P of B given A times P of A by P of B. But this is not very insightful. So let us write it like this. Write it like a table. So we have spam email. We have non-spam email. We have emails containing Nigerian prince. We have emails without this word, right? So these are the four conditions. Now, what is the probability for something to be spam? Probability for something to be spam is out of 10k emails, 100 of them are spam. So the probability for something to be spam is 100 divided by 10k. And probability for something to be not spam is 9900 divided by 10k, right? This is the something for something to be spam or not spam. So let's draw like a table, and now if something is a spam, what is the probability for the word Nigerian prince to be present in that? So if something is spam in this branch, out of the 100 emails, 90 emails have the word Nigerian prince in it, 10 emails do not have. So 90 out of 10 cases, you will have the word Nigerian prince. So 90 out of 100, right? And if you receive spam email, there will be 10 out of 100 emails, 10 out of 100 spam emails without the word Nigerian prince. Now let's consider non-spam emails. There are large number of non-spam emails, right? There are 9,900 non-spam emails, out of which 50 have the word Nigerian prince in it. These 50 are educational emails people are sending to educate others about the dangers of receiving an email like this. So they will have this word in that email, but they are not spam. They are educational emails, right? So among the non-spam emails, 50 out of what was it? 9,900 non-spam emails, right? 10k email, yeah. 50 out of 9,900. They have the word Nigerian prince, and remaining 9,850 out of 9,900, they do not have the word Nigerian prince. Now, what is the question? The question is, if the word Nigerian prince is present, what is the given an email consists of the word Nigerian prince, calculate the probability that the email is actually spam. So if Nigerian prince is already present, then we are in either in this or in this, because this first row is corresponding to emails with Nigerian prince present in it. So now, what is the probability for an email to be a spam and for it to have Nigerian prince? It is 100 divided by, so something to be spam is 100 divided by 10k multiplied by, for it to have Nigerian prince is 90 divided by 100. So this is the probability for something, for an email to be spam plus to have Nigerian prince. But then, can Nigerian prince occur only when there is spam? It can occur in two ways actually. When something is spam, Nigerian prince can occur in the email. When something is not spam also, Nigerian prince could be there in the email, right? So we have to add the case where the outcome is this, the case, this cell. We also have to add the outcome where this is the cell where this is the outcome. So this will be 100 divided by 10k times 90 by 100 plus 9,900 divided by 10k times 50 by 9,900. I hope my calculations are correct. Now we can eliminate a few. So 100 and 100 we can cancel. 100 and 100 cancel. 9,900 and 9,900 cancel. 10k we can cancel from everywhere. So then what is left is 90 divided by 90 plus 50 equal to 90 divided by 140. What is this? 90 divided by 140. 0.64228. So 0.643. So 64.3% chance. So although 90% of the spam emails contain the word Nigerian prince, to classify something as a spam given this word is present, we cannot say that, oh, there is a 90% chance that this is a spam. No, we cannot say that, because there are 50 emails that are of educational nature out of this large pool, which also has the word Nigerian prince. So this is how Bayesian probability actually helps you develop a better email spam filter, for example. The same principle applies when you want to develop some other kind of, let's say, an ML classifier for identifying breast cancer or brain tumor or something like that. So this is the core of Bayesian theorem. So I hope this gives you a fairly good understanding of Bayes theorem, although we'll be covering this in similar detail in the next lecture also. But this is exactly how spam versus non-spam filter should work, because some of these spam looking words can also be present in legitimate emails. So if you now come back to the actual formula for Bayes theorem, basically what it says is, if you are calculating P of A given B has occurred, you should not simply take P of A, because here you have to modify the P of A with some other information that you have. What is that other information? It is these extra terms. So P of A was the prior probability before seeing any data, meaning P of A was the probability for an email to be spam. What was it? It was 100 out of 10k was spam, something like that, right? Now P of B given A divided by P of B is, so P of B is the evidence, meaning P of B is the total number of ways. The denominator here is total number of ways in which an email can have the word Nigerian prince. So there are two ways in which an email can have Nigerian prince. An email can be spam and it can have the word Nigerian prince. An email can be non-spam and educational in nature, and that can also have the word Nigerian prince. So that is P of B. But then P of B given A here in the numerator is the likelihood for the word Nigerian prince to be there in an email given it is a spam email. So that is, in this case, P of B given A. So At the end of the day, if you want to calculate P of A given B, you use this formula blindly, but the intuition behind that is much more logical. So I personally find the formula a bit more confusing. If you draw the table, it's a little bit more intuitive. You can get some more insights. I'm almost certain that if I don't keep using this formula, I'll forget it. But the logic behind this, I will not forget. So if someone were asking me to derive this formula, I can easily derive it out of logic by taking a very specific example. But out of the blue, if someone asked me to simply write the formula, I probably, like right now I can, but maybe after several months or years, I will not be able to. But that is no issue as long as you understand the basic fundamental principle behind Bayes' theorem. So this is a good place to end this lecture. I hope you got a fairly good intuitive understanding of basics behind the probability, conditional probability, and Bayes' theorem. These are all very important concepts in machine learning. So instead of blindly running some Kaggle notebooks or Google Colab or Jupyter notebooks, it is very powerful to know the math behind machine learning. In the past lectures, we looked at linear algebra. Currently, we are going through probability and statistics. So if you have been following with me through in all the past lectures, including this one, it's a really good effort that you are taking, and you are progressing day by day towards your ML journey. So with this, let's wrap up the lecture. We'll see again in the next lecture, where I want to purely focus on Bayes' theorem once again by taking a proper example, so that I'm certain that you're fully clear on Bayes' theorem. Some of the traditional ML models like naive Bayes classifier is literally based on this principle. So let's meet again in the next lecture. See you then. Take care, please. Bye.